Okay, so we've been talking about ratios and proportions and percents and other applications of it. Today I want to take a look at the two main types of relationships that we have. Those relationships are usually referred to as variation. Um, Depending on what textbook you're in and what setting you're looking at it in, it's called types of proportion, types of variation, types of relationships. There's lots of different names for it. And really, what it's describing is how two or more variables interact with each other. Now, by variables, I do mean numbers. Two or more quantities interact with each other. The first type of relationship we're going to talk about is called direct proportion. And when we think of the term proportion or the concept of proportion, this is what we generally think of. It's two variables. We're just going to call them x and y. And when one gets larger, the other one has to get larger in a proportional fashion. Or if one gets smaller, the other one gets smaller, again, in a proportional fashion. Direct proportion is, again, a traditional proportion, is what we refer to as a constant ratio. So what that means is the ratio of y to x equals, we use k to represent that constant. Now, a more useful way of expressing that sometimes is an alternative format is to say that y equals a constant times x. If we're using the term variation to describe this relationship, this is the form we generally look at it in. If we're just comparing two situations, we often use this form because the two ratios have to equal a constant, or each ratio equals the same constant. The two ratios equal each other. For example, we've been looking at similar figures. So if this is 8 inches, 20 inches, and 24 inches. Now, of course, to tell which ones are related, which sides are related, we have to show you the angles. So I'm going to show you that these two triangles are sitting in the same orientation. The ratio of sides, the lengths of the sides, of corresponding sides, are directly related, a direct proportion. The 8-inch side became the 6-inch side. That is our ratio of the length of sides. Well, because this is a direct relationship, that ratio stays constant. I can cancel out the inches. I could have divided by 2, but I'm going to save myself the effort. I don't really need to do that. If I want to find x, x comes from the same figure as the 6. Its corresponding side with the other figure is the 20. And we can cross, multiply, and divide. 6 times 20 divided by 8, 15. So x is 15 inches. So this direct proportion or direct relationship is really the same proportional relationship we've been looking at for the last couple of classes. So the next type of relationship that we can illustrate with proportion And I really don't like it being called this, inverse proportion. I prefer it to be called inverse relation, or inverse variation sometimes. Inversely related. In this situation, in an inverse relationship, if one amount gets larger, the other amount has to get smaller. Again, in a proportional amount. Or, if the first amount gets smaller, the other one has to get larger. Inverse relationships, like I said, I hate using the term inverse proportion. Inverse relationships are often known as a constant product. So in other words, x times y equals the constant. Up here, where it was a direct relationship, it was a constant ratio. Y divided by x was the constant. Here, y times x, or x times y, is the constant. And again, there's an alternate format. That would simply be y is equal to the constant divided by x, instead of, up here, y is equal to the constant times x. Well, first of all, what are some examples that would be inversely related? Well, let's go back to our gears. That gear has 12 teeth on it. We're going to have meshing with a gear that has 8 teeth on it. Pretend those teeth are equally spaced. Gear ratio let's pretend that the power is connected to the larger gear here. That gear ratio is 8 to 12, or both of those numbers can divide by 4 is a 2 to 3 gear ratio. We had mentioned that ratio describes the ratio, not only of the ratio of teeth, but the ratio of RPMs, ratio of torque transfers from one to the other, and a lot of other different quantities throughout this system of these two gears meshing. Let's talk about RPM. If this big gear is turning at 400 RPM, the little gear has to be turning faster. That's why, well, this little gear, if these two teeth mesh together, the little gear goes all the way around. That's 8 teeth. The big gear, it goes 1, 2, 3, 4, 5, 6, 7, 8. It only goes 2/3 of the way around. It doesn't have to get the same number of teeth through the place where the two gears mesh. It doesn't have to make as many turns because it has more teeth per turn. So the larger gear turns slower. The smaller gear turns faster. Well, the relationship here if the number of teeth gets larger, make that look a little bit more like an arrow, the RPM gets smaller. This is an inverse relationship. Now, the term inverse proportion comes from the fact that you can set up a proportion for this. Now, if you don't want to write this next part down, I'll show you an easier way to work with it in just a second. I think setting up an inverse proportion, it's confusing for one, but I think it's not appropriate because the values are not proportional. They're inversely related. Direct proportion is the only true proportional relationship. But anyway, as we look at this, our gear ratio is the 2 to 3. That's our ratio of teeth. Now the RPM, if I let X RPM be the RPM for the smaller gear, that relationship is X to 400 RPM. 2 represents the smaller gear. The X also represents the smaller gear. Well, for inverse proportion, or an inverse relationship, if we want to set this up in a proportion, we have to invert one of the ratios. It doesn't matter which one. If we keep the gear ratio as 2 to 3, the ratio of RPMs gets inverted to be 400 over X. Or we could keep the ratio of RPMs as X over 400, then we would have to invert the gear ratio as 3 over 2. Either way, when we go to solve this, we cross multiply. It'll be 3 times 400 either way, in either proportion, and then divided by 2. We get that X is going to be 600 RPM. Well, that works just fine, but having to remember to invert one of the ratios to make that proportion work, well, it's easy to forget to invert it, and it's kind of confusing. You set up the proportion, and then you flip one of the ratios. We had the 2 ratios here. These are set up both with the smaller gear on top, and then we flip one of them to put them together. Well, that doesn't make sense. A proportion, as we mentioned several times, is supposed to have a relationship in both directions. Those 2 numbers that are horizontal are supposed to go together. The 2 numbers that are vertical are supposed to go together. Well, when we invert one of them, we are destroying those relationships. So let's go back to what we had said earlier about an inverse relationship being a constant product. So I have this gear with 12 teeth turning at 800 RPM. Meshing with this gear with 8 teeth turning at X RPM. The constant here is the number of teeth that mesh from each gear. Like I said, this gear turns 1 complete round. That's 8 teeth that mesh. The other gear only has to go 2/3 of the way around to get 8 teeth into that intersection of gears. So the number of teeth from the first gear is its speed, RPM, times number of teeth. And that's going to be a constant for each gear. So we have 800 RPM times 12 teeth. That's for the big gear. For the little gear, it's going to be X RPM times 8 teeth. So now to solve this, we're going to do the 800 times 12, which is 9,600, equals X times 8. Now we're going to solve that by dividing by 8. 9,600 divided by 8, 1,200. Screw up here. I was using 400 RPMs up there, that's why. Okay, so 1,200 is X, so this is 1,200 RPM. In that situation, it's an inverse relationship. So instead of setting up proportions and ratios, we set up products. Well, there are a lot of relationships other than gear ratios that are like that. We can have pulley ratios. Let's say this pulley here is a 15-inch diameter pulley. And this one here is a 4-inch diameter pulley. And let's say we know that the 4-inch diameter pulley is going at 900 RPM. I want to know what's the RPM of the larger pulley. So this is going to be, again, larger pulley turns slower because it turns one turn, the other one has to turn multiple turns to keep up with it. So larger pulley, lower RPM, that's an inverse relationship. So it's going to be that constant product. So we look at this, we have our RPM times, it's not number of teeth anymore, it's just another way of describing the size is the diameter. Remember, the teeth in a gear is just a way to describe the size of the gear. So X times 15 equals, we have 900 RPM in the smaller pulley times 4 inches is its size, and then we solve. 9 times 400 is 3,600. X times 15 equals 3,600. Then we're going to divide by the 15. X equals 3,600 divided by 15. It is 240 RPM. So this larger gear is going to turn at 240 RPM. Let's look at another situation. And again, now we're going to have to decide. Our first step is going to be to decide, is this a direct relationship or an inverse relationship? Let's say we have a 9 CFM pump can displace, let me do this here. $2,025 gallons of water in 30 minutes. How many gallons can a 12 CFM pump displace in the same amount of time? We'll just say in the same time. So here, we need to look at the relationship. We have the rating of the pump, the CFM. The CFM stands for cubic feet per minute. And the amount of water that's displaced or pumped in 30 minutes. So we need to decide, if the rating of the pump goes up, does the amount of the water displaced go up or down? So if the CFM gets larger, we would expect the water displaced to also get larger. So this is a direct relationship. which means it's a constant ratio. We can set up a proportion. We have the first pump, 9 CFM, gives us 2,025 gallons. The second pump is 12 CFM. Notice the CFM goes on top with the other CFM. And on bottom is going to be the amount of water displaced for both. So we'll let this be X. We cross multiply and divide. 2,025 times 12 divided by 9. We get 2,700. Oh, if the 9 CFM pump displaces 2,025 gallons in 30 minutes, the 12 CFM pump will displace 2,700 gallons in that same amount of time. Bigger pump, more water moved. Makes sense. Look at a situation that looks very similar. But actually is quite different. We have a 9 CFM pump that can fill a tank in 36 minutes. How long would a 12 CFM pump take to fill the same tank? Again, assuming the tank was emptied, meaning it had to be refilled. This looks like a very similar situation. It's very similar wording, but it's very different mathematically. Because here, the size of the pump, if the size of the pump gets larger, the time it takes to fill the tank should get smaller. Bigger pump should do it faster, should take less time. So this is an inverse relationship. Means we're looking at the constant product. So for the first pump, we have 9 CFM in 36 minutes. So 9 CFM times 36 minutes. For the second situation, it's going to be 12 CFM. And we're trying to find the number of minutes, so X minutes. We do 9 times 36. What is that? 324, I believe. Equals 12 times X, or just 12X. We divide by 12. We get 27 equals X. So it would take 27 minutes for that bigger pump, faster pump, to fill the same tank. In many cases, there's more than one, there's more than two variables interacting, so there's more than one relationship occurring. For instance, if you drive 60 miles per hour, you'll reach your destination in, let's see what I want to do here. $12 hours. How long will it take at 80 miles per hour? Assuming you don't get stopped for speeding or anything like that, and that road conditions are fine for either speed. This is an inverse situation. The faster you're driving, the more speed you have, the less time it should take to get there. So these are inversely related. It's an inverse relationship. So we're going to look at a constant product again. So 60 miles an hour takes 12 hours. Now I get asked, how do I know it's 60 times 12 and not 12 times 60? The answer is, it doesn't matter. They both work out the same. Speed times time equals speed times time. 80 miles per hour times X hours to finish. I could have done it the other way. I could have done time, 12 hours times the speed of 60 miles per hour. Would have taken X hours times the speed of 80. You can see that that's going to be the exact same calculation here. 60 times 12, 720, equals 80 times X. We divide by 80, get 9 equals X. That would take 9 hours. Again, let's look at a similar situation. Driving 60 miles per hour. You will travel 400 miles in a given time. How far would you travel in the same time at 48 miles per hour? So here's a situation. We have our speed is getting smaller, going from 60 to 48. The other variable we're looking at is not the amount of time it takes to make the trip now. It's now the distance gone. So if the speed goes down, the distance you move goes down as well. This is a direct relationship. Which means we are looking at a proportion, a constant ratio. So 60 miles per hour gives 40 miles. Now remember, constant ratio, we could also be a constant rate. Proportions are two equal rates or two equal ratios. In this case, it's going to be two equal rates rather than ratios. We're comparing miles per hour to miles. So at 60 miles per hour, we go 400 miles. At 48 miles per hour, we're looking at how many miles we go. Cross multiply and divide. 400 times 48 divided by 60. Giving us 320 miles in that same amount of time. Not quite so dramatic. Well, in some situations where we're trying to drastically increase speed and we're not so concerned about power, we might go through a double relationship like this. Now I drew pulleys just because I didn't want to have to try to draw gears to make this work. But the same thing could happen with multiple gears meshing together. Let's say this here is a 12-inch pulley. This little one here is a 5-inch pulley. The big one here is 10 inches. And this little one here is 4 inches. And this big pulley is turning at 300 RPM. I want to know how many RPM the little pulley is turning at. Well, to do this, I'm going to have to go through 2 stages. First, this pulley here connects to this one. So I have to go through the transition from the big pulley, the 12-inch, to the 5-inch pulley. Now, this is an inverse relationship. Bigger pulley turns slower. Smaller pulley turns faster. So it's going to be that constant product. Again, it doesn't matter whether I do RPMs times diameter or diameter times RPM. Here I was at 12 times 300, so I did diameter times RPM. So I have to do the same on the other side here, diameter of 5 times RPM of, we're going to call that Y, not X, so I don't use the same variables twice. So there we have 12 times 300 is 3,600 equals 5Y. And we divide by 5, giving us 720, I believe, is Y. That means the center pulley here, this little one, is turning at 720 RPM. Now here's the place that a lot of students mess up. A lot of people mess this up, not just students. How big is, or how fast is this pulley turning, the 10-inch? Well, the 5-inch pulley and the 10-inch pulley are on the same shaft. They're connected. Whatever one of them is turning for RPMs, the other one is turning for RPMs. The change in RPM happens when they're connected with a belt. These two are connected with a belt. Same for gears. With gears, that change in RPM only occurs when they're meshing with teeth. So for gears, if the teeth are meshing, then we have the change or transfer of RPMs. If they're on the same shaft, well, then they have to turn the same RPM because that shaft is solid. It's not going to change speeds from one end to another. So both the 5-inch pulley here and the 10-inch pulley are turning 720 RPM. So we find that the 5-inch pulley is turning that speed. We know then what the larger pulley is turning because they're on the same shaft. However, we still need to get to the 4-inch pulley. So we have the 10-inch pulley times the 720 RPMs equals the 4-inch pulley times X RPMs. 10 times 720 is 7,200 equals 4 times X. We'll divide by 4. 7,200 divided by 4 is 1,800 for X. So this pulley is turning at 1,800 RPM. Any questions there? Now, sometimes we can run into a situation that requires both. A 9 DFM pump can empty a, let's do this here, 2,700-gallon tank, 40 minutes. How long would it take 6 CFM pump to empty a let's go 4,050 gallon tank. The different thing here is there's nothing held constant. In our other situations, either the volume of the tank was held constant or the amount of time was held constant. Well, here the time is definitely changing because we're looking for the time, how long it's going to take for that 6 CFM pump to empty the tank. So what we have to do is we have to come up with a situation, a first step where something is held constant. And here, that's going to be the volume of the tank. So our first step is going to be how long for the 6 CFM pump to empty the same tank, 2,700 gallon tank. So that's going to be 9 CFM, 2,700 gallon. Well, 9 CFM in 40 minutes. Smaller pump is going to take more time, so this is an inverse relationship. So 9 CFM times 40 minutes equals 6 CFM times X minutes, where again, X is the minutes to empty a 2,700 gallon tank. So we do 9 times 40 is 360, equals 6X. We solve that by dividing by 6, we get 60 equals X. So that would be 60 minutes for the 6 CFM pump to empty the 2,700 gallon tank. Now we go up to the full situation. We use that last answer to find what we were trying to find, the 4,050 gallon tank. Well, if it's the same pump, which is what we have here, it's the 6 CFM pump, both tanks. This is a direct relationship. The larger tank takes longer, takes more time to fill. So we have a 2,700 gallon tank that takes 60 minutes to fill. We want to know how long it would take to fill a 4,050 gallon tank. Now we cross multiply and divide. 60 times 4,050 divided by 2,700. We get 90 minutes. So sometimes in the problem, for these problems to work, there has to be something that's held constant. If everything is changing, then we have to hold one thing constant and do that intermediate calculation and then use that to finish it off with the final values. I couldn't have left you with a more confusing problem. I apologize for that. But your homework. Now remember, there is a quiz, by the way, from yesterday that is due. So make sure that either you can leave it on the desk there if you would like, or you can submit it in Blackboard, or if you prefer, if you feel better, you can just wait and hand it to me on Monday when I'm there in class. Your homework for today, there's a packet. This is the same packet we started last week. I think we worked on it on Monday as well. But I did repost it on Blackboard in case you don't have it anymore. In that packet is page 234 through 236. Problems 1 through 10 on direct and inverse proportion. So with that, I'll let you guys have the last 10 minutes here to get started on the work if you would like. I'll be on the network to answer any questions.